announcement. One is to the speaker, please give me the paper, clear paper for publication ready, so I can immediately give to our boss. Second, in the back door have some book is for sale, some book is free. Now, have some book is missing, so it's not for sale, so please return back. Has a 7 copy, call what? 0-point energy, 1 copy trapping 0-point energy, and 1 copy new science. And also, please notice the schedule has a little change with the last time I sent you. Okay, when you talk, please use microphone on the back cam very clearly note. Now the next talk is Dr. Stanley Spark from the Navy. His title, Nuclear and Thermal Events Associated with Trading plus Deuterium Co-Deposition.
Good morning.
Maybe sitting here.
The title of my presentation is a nuclear and thermal events.
It's close to micro.
All right.
Yeah.
Nuclear and thermal effects associated with palladium plus deuterium co-deposition. By co-deposition, I mean that we are preparing the electrode by electrodepositing palladium from palladium salt dissolved in heavy water with evolution of deuterium. That means we adjust our potential in such a way that both these events take place. Now the result is essentially a surface which looks like a carpet. Well, there are many people describe that in many ways, but essentially is a rough surface, small globules, submicron size. In addition to, you see the little protrusion here, which are 10th of a micron or less. Now, in my presentation, I shall first give you why did we get into this type of analysis or experimentation. Then I'm going to provide you with a bit evidence supporting the production of tritium, the emission of X-rays, and finally some of the excess enthalpy which we see. Now, in our first experiments, years, that was in '89, we have made a very simple measurement. We measured the temperature at the electrode at heavy 9 and in the electrolyte. We see that indeed there is a difference of about 3 degrees between these two measurements. When you turn current off, you see a rapid increase, something that one would not expect unless the reactions are endothermic. When we put a film behind the electrode, we've seen a pattern. This, as you can see, is a electrode, small wire electrode here. You can see that, in fact, there is a emission of some radiation. Well, as you probably do know, that caused a lot of skepticism. People didn't believe that it is in fact occurring, so we decided to do a little bit more quantitative work. And first I'm going to present you with the results on tritium measurements. Now, we have constructed a cell which was essentially very thin, calibrated part of the urette with the electrode design, which is given here. Essentially what it was, copper tubing, and to which we plated first silver, then we put our palladium, and the counter electrode was tightly arranged coil, tightly coiled platinum. The cell was closed in the sense that catalyst was a large surface catalyst was placed there, and again we could measure the volume of the recombined water. What is very important here is the fact that we analyze, we measure this. Well, essentially what we say that we apply the law of mass conservation in order to determine what should be the composition of the gain or an increase in concentration for a given separation factor. The analysis is done around the electrolyte phase here, and at each time interval we take the sample out for measurements of tritium, we add to make it up, and then a second sample after that to again measure the initial conditions. So this in fact gives us very accurate measurements of the initial conditions that we will carry the electrolysis on. Now the results are rather interesting. They are summarized in here. I'm going to only give you two examples. One in which this has been done on a smooth surface, which is normally obtained by plating at very low current densities, in which you don't have the globules growing. And those are the data as seen. The solid lines are the computed, the open lines, the open circles are the experimental data.
What are you plotting? We can't read it. What are you...
Here's the concentration of tritium, here's the time. So we measure each point here is after a certain period of time, normally 24 hours. They are given here, the dates here. Now what we have also, we measure each time the current efficiency by means of comparing volume in the recombiner. We see here a deviation, increased deviation here, and then we see no activities at all for about 2 weeks, and then we see again activity in here. Now, in order for us to be sure that this is a really production, we inserted the value of Q, that is the excess tritium production, and if we put here at this point about 3 times 10 to the third atoms per second, you can see that we bring the computed and the experimental data very close. Same thing is in the upper region there. In the lower region here, we have another example in which the enrichment is only in the gas phase, not in the liquid phase. That suggests that there are 2 modes of interaction between the tritium on the surface and the electrolyte. In this case, the tritium which was produced at the surface first entered the solution, and then by usual electrolytic process split, divided into, as given by the separation factor S. In here, we have the opposite. First, it went into the gas phase. You can see that in the liquid phase follows exactly the computed values. What does it mean? It means that at least we have 2 extreme cases of the interactions between the produced tritium and the electrolyte. In the first case, it goes and then goes into gas phase. In the second case, it simply goes directly into gas phase. Now, in practice, in the other cases, normally what you see is a both ways, part goes here, part goes there. So essentially, those are 2 critical cases. So far, I think we have convinced ourselves, at least, that indeed we can carry some sort of a nuclear reaction in the in the palladium lattice. So the next step was, well, all right, if there's nuclear reaction, there must be some radiation. There's no way out of it. Well, the first picture which I have shown showed you a couple of screen electrode. Well, but then, of course, this is also open to criticism. Well, maybe it is, maybe it isn't. Maybe you had some interaction with heat or whatever. So we have decided to do a little bit more careful work. And what do I mean by careful work? I mean we designed cells specifically for the purpose of investigation of the radiation. Now, first, of course, we have to be absolutely sure that we control the background. For that purpose, we have two detectors, one continuously measuring background in a shielded cave, in the same shielding applied to our working, where we put our working cell. In the first case, we were looking for only overall picture. For that purpose, we use this arrangement here, which is very similar to the one which we use for the treatment analysis. And we use a one detector, high purity germanium detector. We set up to investigate between the radiation between 15 and 3000 keV. That was the range which we looked at. And we noticed that there is some low increase, about perhaps 1 or 2% over that range. However, when we compress that range to about from 15 to 300, we increase the excess to about 4%, which simply means that the radiation is rather toward the lower energy, not the higher. In order to see that there is some sort of correlation between the soft X-rays and the gamma rays, we have a second arrangement in which we have, again, the germanium detector placed in here, and also the X-ray detector in the same cave. We redesigned slightly the cell in the sense that now the electrode is a flat surface, a flat electrode with the coil open, so you will have less absorption into the metal. And finally, we decided, well, we are going to look for the very soft X-rays, and our cutoff was between 7 to 40 keV. Then what we decided to do, we decided to move the working electrode as close as we can to the detector window. As a matter of fact, the electrode and detector window was separated by thin Mallove sheet, essentially. Now, what are the results of this kind of arrangement? Well, in the first case, we see that in fact the solid circles again are the background. The open are the experimental value. Now, in the first slide shows us, okay, the first one shows us the results of between 15 to 3000 keV, the upper one on the carpet-like surface, and the lower one on the smooth surface. You can see that in the carpet-like surface, or immediately following and during and following co-deposition, we see immediate increase in the gamma count, X-ray, radiation count. It lasts few days. You can see that it's not continuous. It goes up and down. And finally here, it appears that approaches the background. So we decided to add, well, maybe we should add something. So we added here LiOD, some lithium ions to it. And you can see the net results. It's again increased. Now, in the smooth surfaces, it required about how many? 4 or 5 days before we saw the same result. And again, in here, we had to add thiourea to create the conditions that we have seen. Now, to get a little bit more solid data, we decided to, here we present the data recorded by both detectors, that is the X-ray and the gamma rays. And the upper one is X-ray, the lower one is gamma rays. And you can see that there is a correspondence when one picks up the other one also. Now we don't see it here in this one. Well, apparently the radiation and the very soft, we couldn't see probably because of attenuation. But if we increase the current as we have done here, you can see increased both. So it appears that the amount of emission somehow is governed by the current, by the conditions that you impose. Well, finally, of course, as everybody knows, people are asking, well, what is the distribution of energy? You have a count rate, but that is not enough. So we decided to look at it, and here are the data. Oh, sorry?
Another 5 minutes.
This way? No, that way. Yeah. And here you have a count difference per bin. What we have done here, we subtracted the background, and you can see that there is a asymmetry here. That means there is some radiation throughout the whole without any definite pattern, except here. Around 21 keV, we see a peak. Well, that would be associated with PDK alpha. And here again, we see another one. And that was one of the buffering ones because we didn't know what to assign it to. And finally, one of the referees suggested, well, that might be platinum L series. And in fact, remember our counter electrode is platinum. Working in chloride solution, the chances are very good that indeed it will be transferred, and you'll see that. Well, so far, so good. But again, to provide addition perhaps to our own satisfaction, we decided, well, how would it be if we try to synthesize results very similar? So what you have here, the first one is just the usual background, which we see. Here, this one is the thorium oxide spectrum. It doesn't have any special features. And here is americium. And what we did by means of computer simulation, we added that together, and this is what you see here. On the asymmetric background, asymmetric count, you see peaks. One in here, that's B, and A is A. So we feel quite confident that our interpretation is most likely correct. Well, the third aspect of our work is the so-called thermal effect. And here again, we deviated from the accepted procedure in the sense that since we have our reaction starting almost immediately, we have a quite different, well, we can solve by different approach. And the approach we have chosen was that of constructing of a calorimeter with quasi-adiabatic walls. By that's what I mean. I simply mean that we put the cell in a bath, and we put a sensor, temperature sensor, both of them, and we regulate it so that the transfer of heat from cell out or from out in would be zero. That can be done quite easily. By doing that, we can then determine whether we have produced any heat or not, and in fact, how much. Well, the results are again quite reproducible, are reported here. The zero line is in here. So you can see that at the very beginning, we see what one could interpret as negative heat. Well, actually it is not, but because what we plot here, we plot excess enthalpy. That means we are plotting the amount that you read by the writing temperature of a solution, less the integral of I times EC minus epsilon EH times dt. 1 minute? Right. All right. So what I am going to tell you is that, in fact, you see that there is a positive right in here. You have a positive production, and again, you see there are spikes in which there are faster or slower reaction rate. And what, in order to provide summary of it, what I wanted to point out to you, that the pattern is the same, whether we are looking at switching production, it's sporadic and have some, or whether we're looking at the X-ray radiation, it's the same, or whether we're looking at the heat evolution, we see the same pattern. Now, there are lots more to say, but unfortunately, my time is out, so I'll close at this point. Thank you.
I just want you to clarify your tritium work, because you have the separation factor which you plotted.
Yes.
And how much extra were you getting over the separation factor?
Well, the rate of production was roughly about 7 times, the highest one we have 7 times 10 to the third atoms per second. You see, in our case, what we do, we determine the S factor for each experiment separately. It turns out that no matter what you do, it's about the same. We are expressing T over D, so that will be about 0.68 plus minus 0.04.
Can you comment on the any correlation between tritium and radiation?
Well, the only correlation which I can say is that as soon as something is dying out, you add something into your solution, such as beryllium ions, magnesium ions, thiourea, and you restart the process again. So those are the correlations. That's one correlation. The second correlation is the nature, the sporadic appearance. That's about the size. Now, because of that, I believe that one, in order to determine what flashlights to call performance envelope, one has to look at the interface as a separate phase, which is affected by both phases, that is liquid and solid phase. And now, because there are a number of factors coming in, you may build up various instabilities. I'm sorry. You can build up instabilities there, because all you need to do is to have a reaction and a coupling reaction and start.
Okay, since time is so thank you. The new elements formed in electrolytes of light water on palladium.
Good morning. I think it's still morning. You know, I would like to thank to everybody for coming here, and especially to thank to Dr. Bockris for organizing this nice meeting here. Today's lecture will have slight change in title, and as you can see, I call these two zones of impurities observed after prolonged electrolysis of deuterium on palladium. I choose deuterium this time for difference what we have published in Infinity Energy. I believe it is number 8, 1996, where we publish about hydrogen results, where we have less research than what we have on deuterium. I cannot say, as Dr. Spack said, that we really planned those experiments in order to determine some nuclear isotopes or whatever. What we really did, we wanted to produce some well-controlled experiments to see what is the influence of impurities on change of the mechanism of hydrogen or the deuterium evolution, and change of mechanism what will cause some other effects which we were talking a lot during 89 and 90s. I have to say that those experiments were done in 90s previous COMO meeting, and some of those results, if somebody attended that meeting, could see in that meeting. We didn't have clear understanding when we were doing this research, really what are we getting. What we wanted to do is to do well-designed surface analysis and nothing other. But however, during writing of my thesis, we got some mismatch between, I'll say, between two techniques which we use, and main techniques which we use here, as you will see later, are XPS and EDS, or the so-called EDS, or is energy dispersion spectroscopy. Today, I'll talk about results, as I said, from those. Do we have any pointer, Ryan?
Yes.
Yeah.
Good. Yeah. Today, I'll first talk about our XPS results. After that, energy dispersion spectroscopy results. I'll compare results obtained from those two techniques, and I'll try to distinguish differences between those two techniques. And after that, I'll present to you some observations which we have on damage during some similar conditions, and at the end I'll conclude. First, let's see what we had as electrode preparation. This is palladium foil, 99.9% purity, and this is Hoover and Strong palladium. Dimensions were 5 by 5 millimeters and thickness 1 millimeter. We previous those experiments we anneal this palladium at 810 Celsius degrees for 16 hours. Pressure was, I believe, between 10 to minus 6 and 10 to minus 7 torrs. After that, we cool electrode material in argon atmosphere until we have reached room temperature. And looking for electrochemical treatment, what we had is 0.5 amps per square centimeter. And we choose this current because scientists, they start talking already about necessity of high current in order to gain some nuclear isotopes or heat in cold fusion experiments. And we electrolyze our electrodes for different time, 1 hour, 1 day, 1 week, and 3 weeks. And we choose to have 3 of each, that we will get some kind of statistical relation. Counter electrode was platinum gauze, 9 centimeters surface area, and reference electrode was saturated Calmer 1. Solution was, in this case, 0.1 molar LiOD. I believe that was Isotech, that we used that time, all the time, Isotech 1. XPS experimental setup was Perkin-Elmer 5500 spectrometer, source monoenergetic magnesium X-ray. This is, I believe, 1240 something electron volts, soft X-ray, and pressure was we choose different 9, 10 to minus 9 if you didn't do sputtering, and 5, 10 to minus 8 if you did sputtering, because this is pressure of the argon atmosphere inside. Ion gun was 5 kilowatts argon ion beam with size of area of bombardment of 1 square millimeter. IO current was 350 to 400 nanoamps, and this setup for ion gun produced sputtering of some 2.5 to 5 angstroms per minute. Now, here you can see some results obtained from those XPS experiments. I hope that you can hear me well back. First graph represents XPS survey scan obtained. I'd like to read this because I think that maybe at back you cannot see well. Obtained from the palladium electrode electrolyzed for 1 hour in 0.1 molar lithium LiOD solution. As you can see, mainly palladium peaks obtained. No any impurities, no show up of any impurities in this survey scan. However, after 3 weeks, I'm sorry, everything same except that the time of electrolysis in this case was 3 weeks. You can see plenty of impurities around. Now, platinum, main platinum, zinc, iron, and silicon was not shown here because it's covered with platinum, but silicon was observed in some more careful experiments. If after every survey we did some more careful analysis where we had the sputtering of the electrode, and we did sputtering down to 55 angstroms, where you can see for palladium, this is electrode after 3 weeks of electrolysis, again in 0.1 molar LiOD. Graph A is distribution of those two palladium main peaks during first 5 cycles, and graph B is just representing during the last 4 cycles. What you can see here that on the beginning it's almost no palladium there. Usually people think, yeah, carbon is there on the surface, but carbon is only up to some 5 angstroms, not more. Everything other is because of the presence of the impurities. Those are platinum, as I said, zinc, silicon, and copper. Now, after 55 angstroms, we are starting to get almost pure palladium without presence of any impurities. If you look for platinum, those are again main platinum peaks, and if you look for platinum, again this is beginning of the sputtering and end of the sputtering. We can see that increase, as I said, 5 to 7 angstroms is carbon. After that, increase in the platinum peak, and decrease where at the end around 45, 50 angstroms is almost no presence of the platinum there. This can be better seen in this graph, where we have where I have presented basically percent atomic concentration as a function of time of electrolysis and depth of analysis for palladium and for platinum. For palladium, you can see that after 1 hour and 1 day, palladium is almost pure on the surface. However, after 1 and 3 weeks, it's increase of impurities, and we are getting pure palladium after 50 angstroms. For platinum, it's even better seen. No platinum on the surface on the beginning, and no platinum on the surface on the beginning of the electrolysis 1 hour, and main peak around 15-20 angstroms after 3 weeks of electrolysis, and almost no platinum after 40 or 50 angstroms. We have to remember this one, I would like you to remember, because this is important point, that we don't have any impurities after 40 or 50 angstroms. This is how I call first zone of impurities. It's pure surface impurity, and for us was very easy to explain this one because when we did simultaneously we did analysis of our electrolyte, and on the beginning we didn't have almost any impurities there, a slight amount of the silicon because this is alkaline solution and silicon is dissolving from glass, and basically what we get before analysis is there, and what we have is what we have there is basically silicon, platinum, zinc, iron, and copper, and using charge which we knew during this electrolysis, which passed during those electrolysis, and knowing amount of the impurities in the solution in the time integrating this, we could calculate that electrochemical deposition will produce amount of the impurities found on the surface equal to one which will be expected from Faraday law. And that is just saying that basically what we have on the surface is coming from dissolving of the glass, dissolving of the counter electrode, and this is from, we expect it to be from dissolving of the spot welding contacts, which basically are bronze, and always they have some, we have impurities, we didn't take care about that when we were making electrodes. Now, EBS experimental was, this was second spectroscopic technique which we chose, instrument was Joel scanning microscope 6400, equipped with, this basically means detector for X-ray answer which we will get from the during experiment, and this is energy dispersion spectroscope. And this detector can detect elements as light as boron. Source was 25 kiloelectron volts X-ray, and incidence angle, which we used that time, was 90 degrees. Now, what we got from energy dispersion scan, here is written energy dispersion spectroscopy scan of palladium surface after 1 hour of electrolysis, and this one is after 3 hours of the electrolysis.
3 weeks.
3 weeks, I'm sorry, 3 weeks of the electrolysis. As you can see here, no corresponding elements to which we have found to 3 weeks are observed there after 1 hour. Only very pure palladium. Those element captions which you can see are just written here that you can compare. You know that no impurity was there after 1 hour. However, after 3 weeks, you can see a bunch of the different elements: platinum, zinc, copper, iron, calcium, silicon, magnesium, and zinc again. Now you can say those, they correspond, many of those, they correspond to what we have obtained on the surface of the electrode. However, in this table you can see that what we have here is basically, what I type here is basically, I wanted to compare what we have in virgin palladium, and this we got from manufacturer. They dissolve palladium and do ICP measurements, and this is after 1 hour, and this is after 3 weeks. As you can see, main element was calcium, which we really didn't observe with the XPS there. It's only 31% of the palladium there, and I'll later explain why you can see some palladium when we couldn't see any palladium using XPS measurements. We basically, when we were doing those experiments, we thought that we have very similar results. And that was in 1990 when Dr. Bockris went to present some results for Como meeting. But during writing of my thesis, we understood that we have different results, basically, because we understood well how energy dispersion spectroscopy works. Or better to say, I understood well how energy, because Dr. Bockris probably knew it before, but we didn't take enough care about that. And what's difference is really, I want to show here first how we obtain XPS signal. In X-ray photoelectron spectroscopy, what do we have is we irradiate sample, surface of the sample with soft X-ray, which is 1.4 1.2 something kilo electron volts, and that one will knock electron out of the core shell of the atom, and that electron will be detected on the surface. Now, that electron is energy of that electron is characteristic for every atom, but because escape length depth of the electron, it's very short and follows Baer's law. Basically, what we'll get maximum from first layer, less from second, less from third, and in that way, basically, we very fast we stop exit of the electrons, and what we have really, this is universal curve for dependence of escape depth on electron energy, and for most of the for most of elements, those are more organic polymers. This is graph from you can find in any textbook about XPS, and those here are more some organic compounds. Polymers, this part is more corresponding to inorganic inorganic elements. What we have really, it's placed somewhere here: zinc, platinum, palladium, all they have. Somewhere around between 50 and 150, 200 electron volts energies. That means that we have a depth of escape maximum somewhere around 5 monolayers, what will correspond to 10 to 20 angstroms for different elements. Pure surface technique. We just see surface, nothing other. While energy dispersion spectroscopy works works differently. And this is presentation of energy dispersion spectroscopy signal. What we really get here is we irradiate surface of the sample with heavy X-ray beam, which is 25, in our case, 25 kiloelectron volts, and that will produce knocking out in the sample, knocking out of the electron from inner core. Electron from outer core will jump down to fill that gap, and that will produce X-ray emission, which is usually between 0 and 10 kiloelectron volts for different elements. Now, this X-ray, which is detected on the surface, can travel as long as a couple of micrometers. It's no problem, even more. Only stopping signal will happen because for every successful scattering of incident X-ray beam, we'll lose a little bit of energy, and in the end will not produce any more knocking of the inner core electron. This how it's called in books teardrop shape. It's well known in any textbook about energy dispersion spectroscopy, and program can be obtained for either IBM compatible PCs or Macintosh computers to be calculated for different conditions, different materials, different incident angle, and different energy of the X-ray. But what's important here, if you will see, scale here, this is 1 micrometer. Now this is 1, 2, 3, somewhere around 3 micrometers, 2 micrometers in this way. This is now different from what we had from XPS, where we had 10, 20 angstroms escape. Here we have a couple of micrometers.
4 meters. 4 meters.
4 and 4.
Oh yeah, that will be fine. I think that will be short because I starting quarter to 11. Yeah, okay. But I think that I'm right now on the 18th minute. What we have here, I just presented that black one, and I want to calculate some things. What we have is bottom of this cone is 3 micrometers from the surface, and what we have as a diameter is around 2 micrometers. We took and calculate how much will this volume present versus this bottom volume below 1 micrometer. Bottom volume will be responsible for 90% of the signal. Where we have XPS, XPS is somewhere here. But we have to remember now, XPS was showing up to somewhere 50 angstroms, nothing after that. And with EDS, we have observed something beyond that. That's important. Now, we have to remember that in virgin palladium, we didn't observe those things. That means we have some kind of second zone of the impurities. That is what we came as a conclusion when I was writing my thesis. Now, we tried to rationalize the result. First approach was diffusion of impurities from the surface. But when we came to diffusion coefficients for diffusion of metals in metals, which they are 10 to minus 23 to 10 to minus 40 centimeters squared per second, we found that this result here is basically not more than 1 angstrom, and we are talking about length of micrometers. It's not possible cause. Now, congregation of present impurities from, we wanted to see if we know how much we have in virgin palladium, from which volume we will have to concentrate our impurities in our analyzed volume, that we will get the result which we obtained. And that was from 17 micrometers diameter, again, even more impossible than the first case. Last, what I would like to present you are some damage results, which are very important because we observe damage at same depth at which we assume that we have second zone. Shortly, just Johnson-Matthey palladium this time, in KOH and KOD, we didn't observe any difference between those two, as we didn't observe in analysis of light water and heavy water for impurities. Variation of 3 parameters of potential, time, temperature, and we did an optical analysis with differential polarization interference contrast microscopy and scanning electron microscopy. We did first surface, and after that we etched in 30% 1,1 HNO3 HCl. This is recipe of Deborah Rollison from, I believe, Office Navy Research Laboratory. And after every etching, we did new, on that fresh surface, we did new optical analysis. What we have observed is that this is graph. Damage as a function of depth. We don't have any observation of damage on the surface. First damage was observed at 0.2 micrometers, and it almost exponentially decayed down after 5 micrometers. Shape feature of that damage is shown in those micrographs, where we have something as hexagons. This is 2 slides before I will conclude, where we have somewhere we have hexagons and pinholes placed at triaxial points of grain boundaries of the palladium. Those pinholes enlarged at 25 and 50,000. We can see are somewhere around 500 nanometers and of conical shape. When we change potential, we had at minus 0.35 volts, something similar to what you observed there, 3 to 6 pinholes per hexagon. At minus 0.5 volts, same time, 0.5 hours, we have around 30 to 50 pinholes now spreading around in hexagonal in sides of the grain boundaries. And at minus 1 volt, rupturing of the electrode, where you can observe now grains of the palladium. And last slide, which I would like to show, is effect of time, which we had. And here at minus 0.35 volts, always same potential, 0.5 hours, initiation of pinholes, 3 hours, grouping in small islands, 15 to 20 pinholes per one island, grouping after 10 hours, grouping in larger islands, 30 to 50, and after 100 hours, almost 75% of the electrode covered with those, how we call them, pinholes. In conclusion, I would like to say that, first, we have observed by use of XPS surface impurities, how we call them, first zone, which we can easily explain by deposition, electrochemical deposition of the element impurities from the solution which they exist there. We observe second zone bulk impurities using energy dispersion spectroscopy, which is placed somewhere between 1 and 3 micrometers, and which we didn't have any good rationale to explain those results. And I have to say that electrode damage corresponds very much to second zone, which we have observed previously. That will be all. Thank you very much.
Any questions?
What's the total level of your bulk impurity?
What was?
The total level of your bulk impurity.
We had, as I have shown there, I think 30% was palladium and 70% in total whole impurities in that volume which we have analyzed there. As I say, that EDS teardrop shape.
What was the layer? Was it 50 actions or?
No. XPS analysis, they look surface, 15 to 20 angstrom. EDS will look something as this. This will be EDS. Okay, this will be EDS. And EDS has volume of, as you can see, it's, this is 3 micrometers and this is 2 micrometers. This is much larger volume than what the XPS will look.
Okay, thank you, Dora. Next talk is Dr. Michael Swartz from Jet Energy Technology, deuterium production and light water axis entropy experiment using nickel cathode.
It was actually a theoretical paper, and you people are always wiser than me. When I submit 4 abstracts, I always get the one pick that I least expected, so I have to assume you're smarter. So I'm putting in experimental data, and I'm going to have to therefore change the title to possible deuteron production, since this is an experimental section. Basically, what I'm going to show you is how we have managed to get excess heat reproducibly from nickel to determine the activity in the samples. And we have a process by which we can show you where you won't get excess heat, and maybe therefore a small band where you might. We then took these samples that demonstrated excess heat, and therefore we had a pedigree on them. We took them to MIT and looked for electron emission, and we'll talk about those results.
Can you use the microphone, please?
Sorry, is that a little better?
Thank you.
We then took the samples to MIT and looked for beta emission. We have a device there that's semi-quantitative for electron emission, qualitative for photon emission. We did not see results, and I'll show you that. As a result of that, one hypothesis to continue the scientific method is that maybe we're making deuterons and helium-4 in the heavy water, and I'll show you the reason. Now, the reason we begin, first of all, a lot of people are involved. I want to thank them all. We are lucky enough to be able to get samples from a number of people and equipment from people, and Lou Smullen and Peter at MIT were very helpful for doing the beta emission studies. Now, one of the reasons I end up being interested in investigating deuteron production is that in examining all of the papers that are published in this field, as you know, it's often stated that, Thank you. It's often stated this is a dead field based on Dieter Britz's publications, which are here. It's an evanescent collection, and he does not include any of the proceedings We have other studies that Hal Fox has, and we have the positive papers. We've been trying to publish this for a while. This is absolutely not a dead field, but I have failed twice to get this into the ICCF meeting. Now, the reason that I am going to discuss deuterium production is the following. Here are the papers on tritium production. By going through Dieter Britz's papers and doing a scan on the terms triton production and tritium production, we see a whole host of people. Many are here. When I did it on deuteron production and deuterium, there were zip. Well, if not now, when? And if not deuterons, what? Here's how we did the experiments. All of the experiments were done with what I call multi-ring calorimetry, where we use a number of barriers filled with fluids, and then watch the enthalpy go to ring. In that way, we have a closed system, and we're able to get reproducible results. This is the outer chamber. There are actually 4 chambers within here. We use 2 feedback controls, so we have 2 loops, and this is one of the base systems that we have. When we collect the data, one of the things we find helpful is we have 2 or 3 computers at a time for data collection. We have an ongoing I would have submitted another paper to you on thermometry. We have an ongoing thermometry study, and I'll show you one of the results here. But basically, what we find is it's very helpful to have a lot of power supplies when you do this, because one of the things that's never discussed is impedance matching between the solution and the power supply. That's a whole separate subject, and we'll come back to that later. I just show you how we set this up. Okay. In order to do the calorimetry, to find the materials that have good pedigree, to then do the experiments, we do a technique called waveform reconstruction. If you use classical Newton's method, you know that the energy in the solution goes to raise the temperature of the fluid. Some of it goes through the walls, but in fact it heats the walls up too. And if you add the other terms in, you get a much better analysis. And we have a whole paper, hopefully, coming out on that soon. Let me skip these. One of the things we've tried to do is, in addition to using platinum as the anode, I also use gold as the anode. And there are theoretical reasons why it might be more helpful. So what we're going to show you is data on the excess enthalpy prior to the emission experiments for gold and platinum as the anode with nickel as the cathode. Now, we have ruled out, when we do these measurements, we count the input power as V times I. There's no subtraction of the thermoneutral potential. When we calculate the output, there is no addition for gas loss. So anything we measure is a lower limit to what we're actually producing. We've ruled out all of these things. And hopefully when the paper comes out, you'll be able to go through it. And we'll discuss more about it later. Let's skip this through. Here, for example, is the results of one of the experiments.
Raise that a little higher, would you, Mitch?
Sure. What we're looking at here is a series of curves where here is power on this side. This goes with all of these curves, the dashed curves and these power drive curves. And here we see the total integral of input energy in dark black and our total output energy in blue. Now, what we've tried to do is spend a lot of time looking at the noise of our thermometry, the noise of the calorimetry, and even the noise of these calculations. So here's our background noise. It's somewhere between 10 and 100 milliwatts. Here, for example, are 3 resistive heaters used for controls. We see that the input is the solid black line. The output lags a little bit and is lower. And yet for our nickel reactors, we get more out than we get in. So there are 2 ways. What we try to do are controls where we integrate total energy, go through a long baseline, and often what I'll do is put 2 or 3 other cathodes in that tend not to give excess heat, like iron and aluminum. That's not in here. So what you see is a superlinear rise on energy for the reactors, whereas if you look for the resistors, you'll see that they're matched. The slope is matched. So we see it on both power and slope. Now here's one of the results. This is platinum and nickel. And here's gold and nickel. Again, I'd like to measure the noise of the system here. We started off at 100 milliwatts for the noise level. Typically, when we started running these experiments, it would take a settling time with the 5 chambers of about 2 weeks. We're up to 16-bit data collection now with the 2 computers. We're able to actually analyze these samples and get these data out to 2 days now. But you're looking at stuff that took 3 weeks to do in terms of settling, getting the noise down. And here, for example, here's our ohmic resistor. We see a time lag of the output of the power, matches. We see a superlinear rise for the reactor. Here's our input. The lighter line is the output. And here for energy, we see the same thing. So here, this is a linear output. These are the energy curves that go to the right. This is in thousands of joules excess enthalpy. In terms of power, this is a log scale. So we can see here we're putting in about 3 watts and getting out 3 watts. And here we're putting in less. And here we're getting out about 7 watts. Now we found the system very helpful. Almost all of the spectrograms that we do now are this way, where we try to get a long baseline for power. We do it for at least a day or so. And then we're able to drive and integrate the energy as well as power. And I'll show you why I find that helpful. One of the things that can happen if you fail to do that, for example here, for example, I'm sorry this doesn't show up as well as the others. Here we see the noise of the system, here's the input power, and we're driving it below the noise. So we're going to get a false output of excess heat. If you don't drive your system above the noise level in terms of energy, you're going to get the noise out and you're going to think it's excess heat. So for example, in this experiment where we drive below the intrinsic noise, we end up getting a pseudo excess heat, where actually if you correct it, you find out that the time average comes out to 0. But you have to do it right to do that, and you have to measure the noise. Let's jump to some others. Now, one of the things that we find is in terms of power amplification. That is the ratio of the output enthalpy to your input drive power. What we find is that resistors are always here. We're looking at power gain on the left. So 1 is what you get out, what you get in. That's where you'd expect to find resistors, and they're always on this line. The thing that's interesting with nickel is that what we find is when we drive it, the power gain falls. And on an exponential plot, a log plot, we see it's a straight line. Here, for example, this is a platinum system. What we do is this system was cold work nickel wire in the shape of a spiral. We use, this was paired platinum. This isn't the best configuration we have now, but this was the configuration back around '94. And what we find is that the excess heat goes to a peak and then comes down. Now this is, I think this is important because if you get greedy, apparently there's something within the nickel that limits how much excess heat you can get out. Perhaps in addition to the number of favorable sites, like in the case of palladium where we talked about the gamma site, maybe there's a statistical event that can only occur so fast. And in our greed of trying to get more, we're actually coming down the curve. I can tell you the following. I can't tell you when you'll get excess heat, but you won't get it here. Here's another one. As I say, we do a lot of work with gold now. And again, we find this over and over for both gold and platinum against nickel. We have not yet looked at the palladium system. We're going to go back and do that now. But what we always find is that there's a fall off, and we call this the pi notch. So as long as you drive your systems within that peak, you have the best chance of being able to detect excess heat, or if you're looking for the transmutation materials, those. Now, one of the problems we noticed early off, hope this is visible, is that I find all kinds of contaminants end up in the solution. And we've actually driven some of our reactors to try and then centrifuge down the materials. So for example, one of the things that shows up in nickel systems is nickel carbonates and nickel hydroxides. These appear as a green precipitate, And in fact, for example, they can contribute, if you were measuring an open circuit voltage after your measurement, they can actually, by their own concentration polarization, give you an additional amount. We find that any time we take our reactors and drive the anode electrically, we get anodic decomposition, just like you would expect in any corrosion reaction. We see it with the iron controls. It turns out that even some of the plastics break down. When we've driven the reactors, we've had input powers recently as high as 60 watts input. Generally, most of these experiments are 1 to 5 watts input. Generally, the power gain is 3 to 6 for the platinum and a little bit higher for the gold. And we have some other materials that are even doing better. Let me show you some of these precipitates, because I think it's important. In fact, let's go to this one. This is a cold work nickel that we put on mandrels. I try, when I do the experiments, let me tell you one other thing. I tend not to put salt in my solutions. We tend to use distilled water. It comes out at theoretically, as you know, water has 18 megohm centimeters resistivity. As soon as you leave it open to the air, it drops to about 0.9 megohm centimeter as CO2 equilibrates. That, and everything else comes out of solution too. We find that unless we use only high molecular weight polypropylene, all kinds of things leach out. And we're measuring it everywhere now. Now, I'm sorry this looks so bad, but what you see here is auric hydroxide. It turns out that even with gold, which theoretically has less decomposition than platinum, we still see it. And we can see it reproducibly deposit on the cathode, just as you expect with cathodic decomposition. So when you go to do transmutation measurements, you've got to subtract for this stuff, because we've never been able to avoid it. So we took our samples, the best we had, and took them over to MIT as a way of looking for beta emission in February. And I'll show you those results. This is a energy electron emission spectrum. Now, what I'm going to show you is we didn't see any results, but there may be a reason for it. These were metachronous measurements. These samples, which had a pedigree of excess heat, were driven December and January, and we didn't measure for 6 to 8 weeks for some of them. So it may be that there's a signal there, and in addition to being perhaps below the sensitivity of our system, it could also be that it's beyond the time constant where the activity is going to fall off. I can't rule it out. This is the, it turns out that the system is also sensitive to gamma radiation, but it's not quantitative. So we do cobalt, we look at background, we do stripping of the background, and these are the results of our two samples. This is the gold sample, and this is the platinum sample. We could actually put them together. We couldn't see anything. So we're faced with the following. We ran the experiment. We got to a point where we can reproducibly get excess heat, and I can't explain it. So now we'll talk about where we think we are. First of all, I showed you the curves that what it appears to be in nickel is that you get a peak and then you get a fall off. Following some discussions with Ed Storms, who tells me this is not what occurs in palladium. It could be that in palladium, because of internal redistribution, that peak is shifted very far to the left. And that's a whole other story. But basically, we think what's going on is this. Those who followed the paper, I do not believe that this is an equilibrium system. So I'm not certain. In fact, I'm fairly certain that the Nernst equation doesn't hold. Because in that case, you assume there's an equilibrium, and there's no basis yet for us to see it. What we have, if you read the model of quasi-one-dimensional loading, is that we have an equation where the key for getting the material into the metal is this term. And what you're dealing with, it's like blowing up a balloon. If it has a hole in it, you're not going to get anywhere unless your current's high enough, or your wind, and then it'll blow up a little. And what we find is that the loading parameter is a vicious battle between thermal reorientation to the gas phase and entry into the material itself. failure to appreciate that means that you'll never load the material. When we examine those equations, theoretically, we get an equation like this in terms of what we expect to see for the relative rate. So again, with nickel, it's apparently close to the left. If it exists for palladium, it's way to the right, based on some data that we just had shared with us. Let's talk about deuterium and what I think may be going on. Deuterium is probably one of the most fragile molecules we know, fragile nucleons we know. As you know, the proton and the deuteron are quite far separated. If you, for example, look at the relative width of the nucleon in comparison of hard cores, as opposed to the hydrogen atom. You see, in the hydrogen atom, the two nuclei are well fixed. In the case of the deuteron, they're far apart. So one of the reasons maybe people never thought about deuteron production is the fact that they photodecompose at 2 MeV, and they're very fragile. On the other hand, there are some reasons why we may be producing them, and it has to do with the spin states. It is well known that the deuteron in the ground state is a mixture of the 3s1 and the 3d1 states. It turns out that in a potential well of about 20 MeV, the first deuteron state is only 2 MeV down. And therefore, we never think of any other states, but there's one more. There's one located at plus 60 keV above the 0 line. And what may be occurring is the following. We made a hypothesis that what exists is called a fuson. And when materials get into an excited state, normally we never see it because they go back. It's an unstable, metastable state of high energy, and it is unable to come down to the ground state, except in a lattice. In a lattice, where you can have effective coupling. Now, I'm going to go back and forth between helium and deuterium here, so please excuse me. What we think is occurring is that, for example, in the case of helium, that there's an excited state, and when they do, this is a palladium, again, I apologize switching back and forth, that what may be occurring is, normally, you're stuck here, and in a hot fusion system, you can go up a little and generate neutrons. Of course, in a cold fusion system, you don't have that energy, which may explain why we don't get neutrons. And what may be occurring as you go down this 20 MeV is that in the case of palladium, you have a phonon-coupled reaction to the lattice. And those of you who've read Peter Hagelstein's paper and be able to go through it know that there is a basis for timing it. All right, I'm moving as fast as I can. Here's what I think is occurring in the nickel, jumping back to the nickel. We all know that neutrons decompose. 980 seconds, they're gone. They go to a proton, electron, neutrino. If they're around the proton, they only last about 180 seconds. Is it possible that the reverse happens? That with the same rear time constant, we're locally, maybe not often, but when we load the nickel, we have about 10 to the 17 hydrogen within the sample. Could it be that the same reaction, that there's microscopic reversibility, and when the neutron decomposes, it can go the other way and make a low epithermal neutron reacting with these materials? I think it's possible, and I will show you why. In the case of helium, as I told you, these states are well known, and there is reason to believe that once the deuterons, again, I'm switching back to palladium, I'm sorry about that. Once the deuterons are able to form helium-4 in the first ground state, it's stuck because it cannot emit a photon. It's spin locked in that state, and unless you can get this putative fuson reaction to have a coupled reaction to the phonons in the lattice, it's stuck there, so in fact you never see it, it'll go back. I think in the case of deuterium, in the case of hydrogen loaded into nickel, that we might be forming one of these states. Normally, when a neutron and a proton react, they form a state that will not come together. This is the ground state. And I think what may be occurring is this actually should be a, this is actually a 1s0. It may be that that excited state, which is the 1s0 state, in coming down, is able to then drain the upper state, so you make more of it. So in a way, it may be that we have something very close to a laser, in the sense that we have an excited state. If we don't have a pool to take that state down and give us the excess energy, it just fills up, and that's the end of it. We have reason to believe that this is consistent with special relativity. When we calculate, in the case of helium-4, the lifetime of the state, it's consistent. We know that the phonons are about 40 milli-eV in the case of helium. And when we add up the amount of time it takes for that excited state to fall, there is more than enough time to couple to the lattice to eat up that 20 MeV in the case of helium. Now, in terms of how do we look for deuterium? In terms of nickel, if we assume that this putative reaction is true, we have about 2 MeV for the Q of the reaction. It is almost impossible, given the separation factors, to measure any change in the deuterium on the basis of this. When we look at the excess heats that we get, we are only making, deuterium starts off at 0.015%. We're only making about another 0.01% on that. Now, we've tried various techniques. This is what we expect to see. If we're going to measure the deuterium at all, we won't even be able to get to a 1% change until we come up to somewhere between 100,000 and 1 megajoule delivered. As you saw from the data I showed you, the most we've put in so far is 200 kilojoules, which is too low. I'll show you one more thing. We've tried some other experiments in terms of measuring these changes by doing vibrational spectroscopy of the electrodes. This goes back to 1989. We were interested in measuring loading. It's a non-specific way of loading. It turns out that what you're looking at here is frequency. Time is in this direction. This is 50 kilohertz. This is 0. And what we're interested in doing is looking at mass changes within that electrode. And so let me just summarize since I've run out of time. We are able to reproducibly get excess heat in nickel. We know where it does not occur outside of the pi notch. We cannot see any emitted particles for these on a metachronous basis, which means it still could be there, but we're looking too late. We're going to go back and look again. If it's not there, we find that the physics is not inconsistent with fusion of these materials, and in fact is not even inconsistent with the generation of de novo in situ deuterons. And if that's true, we need better techniques to look, because we're nowhere near the sensitivity to look for that. Thank you.
Any questions?
Have you done any analysis of reaction products, other products you talked about? The reason I was asked, for example, to try to tie that back to our nickel work and maybe Dr. Zuno and so on, if you drive as hard as you say and get less heat out or none, you may be driving some of these reactions that are producing the heavier elements, which are negative Q, in which case you can very easily have those reactions going on but no heat out.
That's a darn good point. We have the samples available if you want to test, and I had never thought of that as being the conversion until we came here. It's a good point.
Any questions?
Does your electrolyte has lithium or other?
No.
Just
no.
pure water?
We use distilled water. It's my feeling, maybe I'm wrong,
But
that a lot of the energy that you put in is wasted with the salts. I mean, if you're burning them, that's one thing. You need them. But the fact is, when you put an electric field across a solution, you're going to get space charge polarization. You're going to get cathode fall of these materials. You're going to get all kinds of reactions that do not contribute to getting the isotopic
Have
fuel.
you got carbonic acid there? I mean, is this in equilibrium with CO2?
Yes. Yes, absolutely.
So you've got an electrolyte.
Yes, we do.
Excuse me, could you see the difference between the...
Louder.
Can you see the difference between excess heat with platinum anode or gold anode?
Yes, much more with gold. We're not going to go back to platinum. What we have found is, it'll be in the paper that hopefully will be coming out soon in fusion technology, but we see much higher levels with gold as the anode.
Okay, thank you, Mike.
I almost didn't come to this meeting because I about a month ago or so, I started getting some additional funding from EPRI, the Electric Power Research Institute, that gave me the opportunity to work on some of the time-of-flight SIMS instruments at Charles Evans Laboratory in the Silicon Valley area. And I've been working on their, sort of they're allied with an organization that makes the Phi instrument, which is called a Phi Evans instrument, actually. So we're working on their latest prototype instrument, which they claim is the finest there is. And it's high resolution and very high performance. And of course, it shot the hell out of all my old data in terms of my personal confidence with it, because I didn't have that. I became addicted immediately to the results we could get on this new instrument. So, and in fact, on Monday and Tuesday of this week, I spent both probably 10-hour days on the instrument. So I'm very ill prepared here to be. It's really a work in progress. In fact, I'm back on the instrument next week. But to sort of put things in perspective, I work in a field that's it's allied to this field of cold fusion, although it's not electrochemistry. We use ultrasound to produce cavitating bubbles, which are collapsing bubbles typically in D2O, on a target lattice, which is frequently a palladium lattice, which is about the size and shape, thickness of a business card. It's 50 millimeters square and between 100 and 200 microns thick. And what happens is the cavitation effect is a loading mechanism, we believe, as one characteristic of it. And we're reasonably certain that the palladium loads, although we haven't measured loading in any definitive fashion because the materials becomes damaged. One of the problems that people work with palladium samples here, and then they can take it out of the electrochemical sample and weigh it. And this is sort of one of our foils. You can't really see, but we lose great big hunks of it, so it interferes with our ability to load it. And so we have done two things. We've been chasing the production of heat, which we see in several things. It melts the sample, for one thing, in microscopic regions. And when you add all those little microscopic melting effects together, you get great big holes. It just sort of cuts it apart, perforates it until it falls apart. And that happens very quickly in the system, although our calorimetry is based on steady state calorimetry, and the instrument has a fairly long time constant, 12 to 15 hours in that neighborhood, to come up to steady state. But when we can actually view these things taking place, and frequently the melting behavior begins within the first minute or two in some of the experiments. And sometimes that's such a problem that we never can achieve steady state because we destroy the sample long before the instrument can get up to can reach that steady state time. So over the years, we've looked for nuclear product. We've looked at heat and we've looked at nuclear products. And maybe what I should do here is we started this in, my partner actually started this work in 1989 when he heard Hans and Fleischmann saying you could do an interesting chemistry with palladium and heavy water. And my partner's name is Roger Stringham. This is a photo micrograph, I'm sorry it doesn't show up very good, of a tiny bubble that's collapsing on a metal surface under ultrasound, and it forms the bubble. This one was in a scanner and it got squashed a bit, so it's flatter than it should be.
Which is the metal surface?
The metal surface is down here.
Oh, thank you.
You can't see very well, and the bubble is like this, and there's a collapsing vortex in the middle of the bubble, which is very characteristic of cavitating bubbles. And in fact, when I showed this picture to one of the Navy guys at the Maui Cold Fusion Conference a number of years ago. He said, "Oh, I've seen that bubble. We had them forming on the nozzles of Trident missiles that were when they were first testing the missiles, they were having gigantic bubbles that were forming on the missile nozzle as they shot it out of the sub, and it would collapse and shoot water and material up the nozzle of the missile and quench the ignition process. So they had to change the shape of the system in order to keep these cavitating bubbles from putting out their system. So this characteristic cavitating bubble shape occurs at very large scale and right down to very microscopic scale. I think this one is on the order of a micron or so in diameter. This picture was taken by Larry Crum, who's in the physics department at the University of Seattle. In association, he's better known for his sonoluminescence work than anything else in the cavitation field, but he does other work in cavitation. In terms of bubble physics, just to give you sort of a brief rundown, is what happens in cavitation is you have an acoustic wave that comes in and it has a high pressure, it has a low pressure region and then a high pressure region that follows. So when
You weren't at the screen, so you don't block.
Oh, am I doing that? Okay. When you have when a bubble sees the downward slope of this pressure wave, the bubble starts to grow, right? And it grows down through the low pressure point, and in fact even back up a little bit up the high pressure slope. And it grows it actually increases in mass by a process called rectified diffusion, where mass material from the bubble wall transports into the bubble as it expands. So the bubble's not just, it doesn't have an impervious wall when it's expanding. So when it expands, it grows in mass. So then when it comes back up, so it starts very small, and it has at a one mass, but by the time it's gotten halfway through the cycle, it's increased in mass. So that and of course that mass has brought energy in with it into the bubble. Then when the bubble sees this high pressure region, it collapses very fast, and it collapses in fact it's about a microsecond to go from maximum size to minimum size. And so there's huge amounts of energy concentration in that time frame. And in a sonoluminescent system, this collapse comes down, and the bubble, the key to making a flash of light, which is sonoluminescence in a bubble, is to not push the bubble so hard that it actually comes down and break and ruptures, but to let it come down and bounce off the bottom. And if you don't get a characteristic bubble bounce, you don't get the sonoluminescent flash typically in that. And from our point of view, that's a slightly lower energy bubble system than what we use. We use transient cavitation, where you put a lot of energy into the bubble and you push it right down to complete collapse, where it goes through this vortex formation. And what happens in that, in sonoluminescence, the best work that we can refer to is the sonoluminescence bubble physics that's been quite the passion of a lot of the physics community these days. And temperatures in the bubble, due to this collapse, which is an adiabatic so fast that it's adiabatic, so that all of the energy, there isn't time for energy to transfer out of the bubble through the bubble wall. And also a shock wave comes in. It's supersonic, or it's at the speed of sound. So there's a shock wave that comes in that adds energy to the system. And the sonoluminescent physicists say, well, the minimum energy in this collapse is on the order that would create bubble temperatures of 10,000 degrees. And depending on whose numbers you'd like to follow in the field, the higher energies in the bubble range from 50,000 to 50 million degrees in the bubble. And we're perfectly happy with that 10,000 degrees in that that's ionizing temperatures in the bubble, so that we're separating the water molecules. It's basically water vapor in the bubble, and we're splitting the molecule and ionizing the hydrogen atoms. And then via this mechanism, if those hydrogen atoms if indeed what's in this bubble at this point is a dense plasma, and if you believe Larry Crum from University of Seattle, the density inside of these bubbles at the point of collapse is greater than 13 grams per cubic centimeter.
You can't see the graph.
Can't see it, sorry. So that is it's a very high density plasma-like substance, and we think that and it gets directed at the surface. And we believe that's a mechanism for loading, and in fact we can observe as you watch the palladium foil in the system, starts out nice, perfectly flat and planar, and it quickly starts to crinkle up and deform as it's becoming loaded, distorted from the loading. And we have had one of the scientists from NRL who was working with us for some period of time, took samples back to NRL and using X-ray diffraction determined that it was a loaded lattice as well, very highly loaded lattice. So that's the extent of understanding of loading that we've had. What we have done in terms of heat, in the just over the last year, we were funded by EPRI to run a series of experiments to demonstrate how reliably we could reproduce these effects. And so we ran probably 75 or 80 experiments at SRI, with the SRI team there taking the data. And we mostly tried to just hold their hand and make them run the experiments, although we had more hands-on than we had hoped. But to give you an idea, all of our experiments are run as a calorimetric experiment, and we have an internal joule heater calibration in the system. And so what we do is we're doing steady state calorimetry as well as mass flow calorimetry, although we rely on the steady state calorimetry as the method. And this is a plot of the internal joule heater calibrations that we see on it. So when we have the system there, if we put 100 watts in the system, we see it rise up to a steady state and stay that. And one was slightly more than 100 watts, and we put 200 watts in, we see that these lines come up and find a nice steady state. And at 300 watts, we're pretty close. When we went and plotted the data of the total, all the experiments, I'm kind of hustling along to get onto the nuclear parts, but we plot this is the data from the SRI report, which is about to be published by EPRI as an EPRI technical report. We have a line here, which is energy in equals energy out, and some of the square marks on the line are joule heater calibrations on the things, and the rest of the spots are experiments that ran. And so an experiment like this, where we were putting in something like 180 watts of energy into the system, we were measuring about 310 or something of that nature output. Whereas on these experiments here, where these were all mainly palladium heavy water experiments. There were very few titanium. This is a titanium experiment. There were a number of these experiments that make the best controls because they were palladium heavy water experiments that we expected to work, and they didn't, and they fell on the calibration line. So we have a good scatter of success and failure in the same system. Some of these are things like we were trying, there was quite a range of different palladium materials that had been received from different suppliers and with different treatments. Some were annealed and some weren't. Some samples had boron added to them because there was an idea that boron might be engaged in the reaction, it would improve it, and the boron experiments all fell. In fact, I think those are the 3 boron experiments. So we think that was fairly robust evidence that we can quite reliably produce excess heat. Not every time, but over the course of a week, we could probably do it 4 out of 5 days if we were asked to. And the quest at SRI was to look for helium. And the reason why we were looking for helium at SRI is that we had run some samples with Tom Plater and Dale Tuggle, some experiments at Los Alamos a couple of years ago. And we had lots of problems in terms of calorimetry and things, and we were not as good at the apparatus as well accustomed as we thought. But we had taken samples in stainless steel, fairly high quality sample bottles that were actually belonged to Los Alamos. One day we should give back. And we sent those samples to, originally we had planned to do the mass spectroscopy at Los Alamos, but their mass spec broke down on the first day we were there. So we kind of got mucked up there. We took samples, a very few samples. We sent them to Rockwell International's lab in Canoga Park. And lo and behold, this top one was a run which came out of the reactor, a gas sample from the reactor, which didn't produce any heat effects, and it was a very low helium concentration. This one, which was a run which had run for about a little under 20 hours, that we call short, had produced a small amount of helium-4. It was curiously had produced a fair amount of helium-3, which we found quite mysterious. I'll talk to you about that in a minute. And then this other one, which was a long run, had produced 500 parts per million helium-4, very low helium-3. The argon that we were using in the system, we sort of infer, was at about this level from one of the samples that was also a dummy run. Air, I just put that as in, we didn't measure this, but this was, we actually had measured this argon and our own argon is typically what we see. And in fact, the argon we use now, we measure it, it's down around a part per billion helium in it. So what happened is we saw 500 parts per million. That represented about 10 to the 18th atoms of helium produced in the experiment. And it was very low in helium-3. In fact, it was at least an order of magnitude, maybe close to 2 orders of magnitude below natural abundance ratios for helium-3, helium-4. So we think that ruled out a contamination source. We also looked at the neon-22 helium-4 ratio in the sample at Rockwell, both neon isotopes accompany helium normally and are observable in almost any source of helium found. And we use neon-22 because we have argon in the system, and we didn't want to see doubly charged argon-40 show up and interfere. So the neon-22 was below the level of detection at Rockwell, even though the level of detection was several orders of magnitude better than would be necessary to see the neon-22 in the system. So we have no idea how low it was, but it was very low. So we think that was good evidence for that the helium there was new origin. The reason what had led us into this work is that we have done a number of experiments before this where we had been sending samples initially to a mass spec lab at SRI, not associated with the cold fusion group there. And we had seen consistently about anywhere between 8 to 50 parts per million helium showing up in those samples over quite a number of samples. Then we started sending samples to the U.S. Bureau of Mines in Amarillo's helium lab, and we had seen in the neighborhood of 60 parts per million samples coming out of that work. And so then we did these experiments, and we saw this great big one here. And then we've recently been at SRI running experiments, and I'll talk about that in a minute. This helium-3 experiment, at first we thought this was helium-3, and we imagined that's all it was, and Rockwell held onto the sample, and a few months later they measured it again, and lo and behold, the helium-3 was up in the sample. So they held onto it for a longer period of time again, and measured it 2 more occasions, and the helium-3 kept increasing, and when we plotted the increase in helium-3 in the sample as a function of possible tritium decay, and it pointed right back to the day of the experiment. So I think we're inferring that tritium got into that sample bottle at the time of the experiment. And we don't know exactly, where it came from. We were working at Los Alamos, where people worry about tritium drifting around, but Tom doesn't seem to worry about it. He's still kicking anyway. So we also, down at Rockwell, we looked at helium in the metal. We did bulk analysis of some samples of the metal. And we saw, I'm sorry I don't have the virgin samples here, but typically the virgin palladium has 10 to the 7th atoms of helium in it. Rockwell has done years and years of measurement of helium in metal sets there.
Are these per cc off the gram or what?
What, in this? Well, let's see. This is all in atoms up here, right?
Okay, but what's it per electrode per cc?
Oh no, there's sample. Well, these were in 50 cc sample bottles, right, of gases that came off of the system. Our system is pressurized with argon, and we over D2O, and we take the gas off. the metal samples are, you know, a few milligrams. You know, this one was 10 milligrams, this one was a titanium sample, 8 milligram samples of metal that was put in a mass spec and completely vaporized in the mass spec. And that's the Rockwell method. They've been looking, their business for the last 20 years has been examining the helium in metal samples which result from neutron irradiation of those samples, so from an in-alpha reaction being produced. So they're very confident that they can see helium in metals and have a lot of a great database of hundreds or thousands of analyses of various metals that they've done. And typically, you know, metals never show more than around 10 to the 7th if you ion implant metals with helium at Rockwell. These foils, which are 100 micron foils, which they coincidentally are frequently used, which we use, they would find in the neighborhood of 10 to the 8th in ion implanted material. So it's a bulk analysis. So, you know, we saw some small increase of helium in the sample metals. But, you know, honestly, we've never had a resource. Everyone here talks about lack of resources, and we suffered from that as well. 3 minutes, oh, goodness gracious. All right. Well, we started doing SIMS work. And first thing I did was dynamic SIMS work at Lawrence Berkeley laboratories at the National Institute for Electron Microscopy. And we saw some very unusual things with the dynamic SIMS. Resolution was poor. I wasn't very happy with the work, and I talked about it a little bit. I lost one of my spectra that I brought along. I just sketched one out. One of the things we saw that was very odd, which we still are trying to figure out, is this is what the sort of rough isotope pattern for the 5 isotopes of titanium looked like. We looked in one of our palladium samples in one of the hot melted zones with dynamic SIMS at Lawrence Berkeley labs, and we found that titanium-48, which is usually roughly 70%, and the 2 isotopes 45 and 46 of titanium, which are both around 7%, that on the corner of the sample we could find that the trapped titanium and palladium was in normal isotopic ratio. However, next to one of the hot melted sites, we found that the titanium 47 and 48 peaks had switched positions in the sample. And it's still, to this day, a great mystery to us, and I must admit we haven't seen it again in our current SIMS work, but I think that's a characteristic of the spottiness of this phenomenon. We ran experiments last summer also with Jean-Paul Vivirian from France, who was in our lab working, and he took a sample of, he took a sample of material that had melted dramatically back to France with him. He took it to a SIMS lab in Lyon, France, where they had time-of-flight SIMS, and they put it in the time-of-flight SIMS, and this is sort of roughly this is the ratios of the palladium mass range, and these are pretty much right on the button for palladium isotope ratios. On the corner of the sample, we looked in the melted zone of the sample, and suddenly palladium-4 was way the hell up there. And that sort of got us turned on to hunting for anomalies in the palladium. And we're working on that. So now what we're doing is we're working at Charles Evans. And to show you sort of the kinds of better resolution, Charles Evans, this is the deuterium H2, you know, the D versus H2 resolution that we can achieve fairly commonly in the instrument, so we can resolve. That's one example of the resolving power. In titanium isotopes, here's another example of the resolving power for the titanium group. So we can see here on titanium 46 that wouldn't have a titanium hydride because there's no titanium in front of it. We don't see a hydride peak. However, here at 47, you can clearly see the titanium hydride sitting there on the right-hand side. And here on titanium 49, which is this, which follows the big titanium 48, you can see that the hydride's the predominant peak in that case, and that the 49 peak is, you know, at lower resolution would be buried in that big hydride signal. And then here's the titanium 50. We can clearly see the titanium hydride's hydride, titanium hydride here in the main peak. So we've decided to go for resolution, high mass resolution on our work and try to sort this out because there's an awful lot of isotope multiple ion interferences that one has to sort out in this work. But you know, to conclude, we are seeing many similar effects to what Dr. Mizuno has seen and what George Miley has seen. And you know, and I was extremely happy to hear Dr. Mizuno comment that he sees these effects in in cathodes that don't produce heat, because we have also seen that, and we had hoped that those would be good controls, and they appear not to be good controls. So, you know, we're still seeing the anomalies. And currently, our program we do have palladium samples from some of the best groups in this field, who, you know, cathodes that have produced heat from Europe and from the U.S. and from Japan that we're looking at in this, and it's an ongoing effort. And I have tons of spectra and things with me here in the meeting and materials, so we can chat since it's a small group.
I have a couple of questions.
Sure.
One is a comment on the tritium, and you expect some helium-3 because you have tritium in the D2O, so
Right.
there's some background. Okay. So,
Yeah, but we didn't see it in all of the samples.
Yeah.
So there was just
so
that.
That's a little unusual.
It was
but-
that one sample. The other samples were the same materials.
But at some level, you're going to see it.
Right. Yeah, we don't know where it came from.
Yeah. The other question is on the ejecta that you have in some of those other samples. Have you looked around the ejecta for?
We have, and in fact, that one of the things 2 years ago when I went to Lawrence Berkeley Labs and sat down for the first time in my life at a SIMS instrument, I thought I was at a typical SIMS instrument, and it had a wonderful scanning electron microscope attached to it. And I said, oh, this is great. I can do electron microscopy and SIMS simultaneously. Just hit a switch and turn one machine off and the other one off. I've subsequently found that those are extraordinarily rare instruments, and the visual resolution that you have for samples is very poor generally in SIMS. So it's so poor that it's not at the scale that we require on our samples to find what we call little volcanic-like ejecta events, which we think are our prime candidates for SIMS. So we're reduced to doing kind of a systematic survey of a lot of spots across the material in hope that we will find it. And in fact, that's working. We in some of the latest data, we have done 10 sample sites, 100 microns apart, and the samples are 8 microns across, and we are tracking isotopes up and down across that pattern of things. So it clearly shows that the distribution of material there is quite uneven in material. It's also near surface.
So I just wanted to get quite clear with you, in the sonoluminescent experiment, your heat is how many watts per cc do you produce?
Or how many watts per cc?
Or whatever, some measure of the...
Well, the excess watt, we're typically seeing in these samples, which are 3 grams of palladium roughly, we're producing steady state heat is anywhere between 100 and 180 watts excess on a steady state basis.
About 30 watts per cc.
Something. Well,
No,
is that what that works out to? Sure. This is yeah.
per gram. About 30 watts per gram.
Yeah. Okay. That's
Yeah, you mentioned the temperature in those collapsing bubbles. What's the pressure?
Well, the pressure, that's a tough one. Do you know, Barry, what the typical pressure in a sonoluminescent bubble is considered?
Oh, geez,
It's huge.
Like other things, depending on whose model you believe.
Right.
Thousands
If you believe Larry Crum of Seattle, this material is large, is a plasma-like material that's at 13 grams per cc density, which what pressure does that equate to? That's a metallic density. So it's a tough call to what the pressure is. Extraordinary pressures. Okay, thank you. George.
I just wondered if you try to compare this to any of the plasma focus stations that, for example, Sun Boston, at Fair Mountain, I did low of it. That's another way of having a dense plasma plant. It seems like they should end up being fairly similar.
It may well be, you know, we're struggling with what we have, and we haven't had a chance to compare it too much with other work. And we also work, I can tell you, you know, that we work in a variety of metals. We see the effect profoundly in palladium, which is handy to work with. Titanium is very good. We tried what we thought would be a blank, a material that should not load a while ago, which is silver. They have made oodles. Thank you. All right. The last round is the Bockris using information sensing, low energy nuclear reaction and electrolyte cell.